Now we will learn about the means and variances of random variables. So here we will learn about the mean of a random variable, and we already studied about there are two types of random variable. One is discrete and one is continuous. And it's saying that discrete random variables, we will follow the same strategy we used with quantitative data, that is describe the shape, center, spread and identify any outliers. So how we get the mean of the discrete random variable? For this we will use, suppose that x is a discrete random variable whose probability distribution is, these are the values and this is the probability. So to find the mean, or we call it as expected value of x, we have to multiply each possible value by its probability and then add all the products. So we write it as like this: mu x is equal to expected value of x is equal to x1 multiplied by p1 plus x2 multiplied by p2, and similarly we will go on, and in general we show it as summation sign xi pi. So here is an example, and it's saying that baby's health at birth. So the probability distribution of x is equal to, Apgar score is shown below. We have to show the probability distribution for x is legitimate. Make a histogram of the probability distribution, describe what you see, and Apgar scores of 7 or higher indicate a healthy baby. What is probability of x greater than or equal to 7? So this is our data. We got this. So first we have to show the probability distribution of x is legitimate. For that we have to do, all the probabilities are between 0 and 1. These all are 0 and between 0 and 1, and they add up to 1. And this is a legitimate probability distribution, which is, here we can see how it can be shown. So make a histogram probability distribution. So here we can, we made this histogram, and it's saying the left skewed shape of the distribution suggests a randomly selected newborn will have an Apgar score at the high end of the scale. There is a small chance of getting a baby with a score 5 or lower, because here we can see that this model is kind of skewed. So here these values are much higher in number than these. So now it's asking about the Apgar scores of 7 or higher. So we will get the px greater than, and we will add 0.908, and we would have a 91% chance of randomly choosing a healthy baby. Now on the same data, if we have to calculate the mean of the random variable and interpret it in context, so we already know what is the formula. We will get xi pi and do the summation. So for 0 it would be 0, then 1 multiplied by 0.006 plus 2 multiplied by 0.007 plus 3 multiplied by 0.008, and we will do same thing till 10. And the value is 8.128. So the mean Apgar score of randomly selected newborn is 8.128. This is the long-term average score of many randomly chosen babies. So the expected value does not need to be a possible value of s or x or an integer. It is a long-term average over many repetitions. So statistical estimation. Suppose we would like to estimate an unknown mu. We could select an SRS and base our estimate on the sample mean. However, a different SRS would probably yield a different sample mean. This basic fact is called sampling variability. What does this mean? First of all, when we call it statistical estimation, then we are talking about the sample, and here it is saying unknown mu. Mu is the population parameter. So it is saying that if we are taking the different samples from the population, then a different SRS would probably yield a different sample mean. So each sample there is a good chance that each sample has different mean, and this fact is known as sampling variability. The value of statistics varies in repeated random sampling. And to make sense of sampling variability, we ask what would happen if we take too many samples. So here we will see an example, and we earlier learned that using sample statistics value, we can estimate population parameter value. So statistic is any number that summarizes the result of the sample, whereas parameter is any number that summarizes the result of the population. Example is a new variety of corn is being tested to determine its yield in bushels per acre. So mu is equal to mean yield of the corn variety in bushels per acre. But we cannot go in all fields and get the yield. So what we did, we got 15 plots and got their yields. So we got these yields. And what is the mean? Its mean is 123.8, and this is estimating mu, that is population mean. So it is telling that 123.8 mean is estimating for population mean. Now the points are x bar, that is the sample mean, not expected to equal mu. Different plots and condition give different yields, that is different x bars. And x bar varies from one sample of plots to another sample of plots. And the larger the sample size, the closer x bar should be to mu. So here we will learn about the law of large numbers. What does it say? It says if population has a finite mean mu, x bar, the mean of a random sample, is used to estimate mu. Then as the sample size increases, x bar gets closer and closer to mu. And this is the law of large numbers that can be proven mathematically. So here are the rules for means, and these are rule 1, 2, 3, and we can see that first we will take rule 2. It's simple. It's saying that if x and y are random variables, then mu x plus y is equal to mu x plus mu y. And when we will subtract, it would be mu x minus mu y. Whereas if x is a random variable and a and b are fixed numbers, then mu a plus b x is equal to a plus b mu x. We will understand this by an example. So it's saying the crickets living in a field have a mean length of 1.2 inches, and we want to know the mean in centimeters. So there are 2.54 centimeter in an inch. So the mean length in inches is multiplied by 2.54. So it would be 3.05 centimeter. So here we are using rule 1 with b is equal to 1.2. But in this example, we are not taking any value for a. So variance of a random variable, because we use mean as a measure of center for discrete random variable, we will use the standard deviation as our measure of spread. The definition of variance of random variable is similar to the variance of a set of quantitative data. So here we can see that this is the sample or example for the value and probability, and mu x is the mean of x, and the variance of x is x1 minus mu x whole square p1 plus x2 minus mu x whole square p2. Similarly, we can show this formula like summation mu xi minus mu x whole square into probability I. To get the standard deviation, we will take the square root of the variance. So here we can see an example of Apgar score, and we are considering the random variable x is equal to Apgar score, and we have to compute the standard deviation of random variable x and interpret it in the context. So what we did earlier, we got the mu x earlier, so here we are doing the same thing, and we got the value of 2.066, and for the standard deviation we will take under root, and it is now 1.437. So now we will see rules for variances and rules for variances and standard deviations. Rule 1 is if x is a random variable and a and b are fixed numbers, then variance a plus bx is equal to b square sigma square x. What does this mean? It means if we add a constant a, we are adding here a to every value of a random variable, then its variance is unchanged. Like we were seeing earlier, there are 1, 2, 3, 4, 5, 6, these type of values were there. So if we are going to add plus 2, plus 2, plus 2 in each number, then it will not be, variance will not be changed. But if we multiply it by a constant, then its variance will be multiplied by the square of that constant. So you can try this in a small data, like 3 or 4 values you can take and see if it is right or not. It is right though. Rule 2 is if x and y are independent random variables, then variance x plus y is equal to variance x plus variance y. Similarly, but here the thing is different. Earlier in mean, what we were doing, x minus y would be minus. But here in the variance, it's again plus. So there is the proof for this formula. So, but this is that is out of course. But we should remember that if x and y are independent random variables and we are looking for the variance, so when we are adding or subtracting, we have to add both values. Now, what is rule 3? Rule 3 is saying that if x and y have correlation rho, then here it was independent random variables, whereas here it has correlation rho. Then what would be variance? Variance would be variance square sigma square x plus sigma square y plus 2 rho sigma x sigma y. Whereas when we are subtracting, here it's adding, but this value subtracting here. So it's sigma square x plus sigma square y minus 2 rho sigma x sigma y. Now we will learn about the general probability rules. So probability rules, we already learned about them. We will see again, that is, our study of probability is concentrated on random variables and their distributions. Now we return to the law that governs any assignment of probabilities. First rule is the probability P of any event A satisfied 0 to 1. It should be from 0 to 1. Rule 2 is if S is the sample space in a probability model, then probability of sample space is equal to 1. Rule 3 is if A and B are disjoint, that is P, A or B, then probability A plus probability B. Rule 4 for any event A, that is probability of complementary A is equal to 1 minus probability of A. Fifth rule is if A and B are independent, that is probability A and B, then we will multiply both probabilities to get that value. So here's a Venn diagram we earlier seen, and it's showing two disjoint events and two events that are not disjoint, that event A and B consisting of outcome they have in common. So we know that addition rule for disjoint event is simple, and what we have to do, if they are disjoint, we can add their probabilities. But here addition rule for unions of two events, for any two events A and B, what we will do, that is P, A or B is equal to PA plus PB minus probability of A and B. Why we are subtracting? Because if we are going to take it again, then we are adding this part twice. So what we will do, we will subtract it once. Now the conditional probability, the probability we assign to an event that can change if we know that some other event has occurred. This idea is the key of many applications of probability. When we are trying to find the probability that one event will happen under the condition that some other event is already known to have occurred, we are trying to determine a conditional probability. The probability that one event happens given the other event is already known to have happened is called conditional probability. When probability of event A is greater than 0, the probability that event B happens given that event A has happened is found by probability of B given A is equal to probability of A and B divided by probability of A. So the general multiplication rule is that the probability that event A and B both occur can be found using general multiplication rule, that is P A and B is equal to PA multiplied by PB given A, where PB given A is the conditional probability that event B occurs given that event A has already occurred. Now earlier we have seen we got the conditional probability formula, that is PB given A is equal to P A and B, that is PA intersection B divided by probability of A. Now by this if we can write this, then we can also write a different formula, that is probability A given B, that B already occurred, is equal to, what would it be? Probability of A intersection B divided by probability of B. Now with this formula we know that P A and B is equal to PA given B multiplied by PB, that is probability of B. So because this is the formula, so we can substitute this value here and we will write PB given A is equal to PA given B multiplied by probability of B whole divided by probability of A. So this is the Bayes theorem. So the tree diagrams, probability problems often require us to combine several of the basic rules into a more elaborate calculation, and one way to model chance behavior that involves a sequence of outcomes is to construct a tree diagram. So we are considering a flipping of coin twice, and what is the probability of getting two heads. Here is the sample space, that is head head, head tail, tail head or tail tail. So for probability of two heads is equal to 1 by 4. Now we will see it by tree diagram. So first what we started with tossing a coin, and when we make this tree started with, here we will go with one arm and this would be the other arm. Always we will add when we will add both arms, the sum would be 1 because the probability sum is always 1. Now here we can see if we are going to toss a coin, either it could be head or tail, and what is the probability? 1 by 2. Now we got head and now we tossed again, second tossed, again we got head, that is 0.5 probability, or tail, that is 0.5 probability. Again from the tail part we did the same thing. So this is the tree we made for this problem. Now it's asking for the probability of two heads. Where are the two heads? So we can see one head is here, one head is here. So to get the probability of getting two heads, we will multiply these two probabilities. We will get 1 by 2 into 1 by 2, that is 1 by 4. So here's one more example of tree diagram, and Pew Internet and American Life project finds that 93% of teenagers, that is ages 12 to 17, use the internet, and that 55% of online teens have posted a profile on a social networking site. So this 55% is included in this 93%. Now it's asking what percent of teens are online and have posted a profile. Now we will see it. We are going to make a tree diagram. So we are randomly selecting a teenager. There is a probability of 0.93, that because we know that they are using internet. So if it's yes, then what is the probability? 0.93. Though it is not given what is the probability of no, but we know 1 minus 0.93 is 0.07. So we will write 0.07 for no. Now our tree is growing, and it is asking for the online. So if there is online profile, what is the probability? It's 0.55. Now they don't have online profile, so what is its probability? 1 minus 0.55, that would be 0.45. Now here we already got no, so again we will got no, so one whole probability is given to this and 0 to yes. Now we will see the question is asking what % of teens are online and have posted a profile. So online and posted profile, what it be? 0.93 multiplied 0.55. What is the answer? 0.5115. I think now your concept is pretty clear from this example, but we will see one more example later. So Bayes rule, an important application of conditional probability is Bayes rule. Earlier we have seen that Bayes rule. It is the foundation of many modern statistical applications beyond the scope of the textbook. And suppose that a sample space is decomposed into k disjoint events, that is A1 to AK, and none of which has zero probability, such that PA1 to P plus PAK is equal to 1. So let C be any other event such that PC is not 0, then what would be PA given C is equal to PC given A multiplied by probability of A. And now we are dividing, because PC A1, because it is saying that there are k disjoint events from A1 to AK and none has the probability 0. So we have to include all these values in the denominator. So what we will do, PC given A1 multiplied by PA1 plus PC given A2, PA2, and we'll go till PAK. However, it is often intuitively much easier to work out answers with a probability tree than with these lengthy formulas. So we saw how tree diagrams are much easy rather than doing by the formula. So now here is one more example, and it's saying that if a woman in her 20s gets screened for breast cancer and received a positive test result, what is the probability that she does have breast cancer? So this is the diagram we got, and it's saying mammography has been done and disease incidence is cancer. Its probability is 0.0004. That's pretty low. So what would be the probability that it is not cancer? It would be 1 minus 0.004, so it would be 0.9996. Now it's saying that if there is cancer and it is positive, its diagnosis sensitivity is 0.8, whereas 0.2 probability is of negative, that is a false negative. But when we study about the no cancer, here we can see we have the probability of 0.1 for positive, whereas for the no cancer with negative testing is 0.9. Now it is asking about the probability that she does have a breast cancer. So in which condition she can have breast cancer? There are two options of the positive. This positive and one is this positive. So we will see how we will do apply Bayes theorem. So here we can see A1 is cancer, A2 is no cancer, C is a positive test. So P cancer given positive. So now we have to get this value. So we multiplied 0.8 into 0.0004. But what is our sample space here? What we are going to divide it with? It would be 0.8 multiplied by 0.0004 plus 0.1 multiplied by 0.9996, because this is also positive. So we will also take this condition, and this is the Bayes theorem we earlier studied about, and its value would be 0.3%.